Hi, everyone. This is going to be part 2 to the Unit 2 notes. To start off with, I'm going to talk about Vesper theory. Now, in class, we've already gone over how to utilize the Vesper chart, how to identify bond hybridization patterns, and all of that fun stuff. So if during the course of this video you're confused, it's probably because you don't have that Vesper chart out and you're not referencing it. So make sure that you have that out so that you can understand what I'm saying as I go along. To talk about Vesper theory, it stands for valence shell electron pair repulsion. So basically, electrons are going to try to maximize the distance between them to minimize those repulsive forces. Okay, so as that happens, as the electrons are trying to maximize the distance between them, you get bond angles as the atoms orient themselves around one another. Okay, so down here on the bottom left, the angle between these two atoms, these two, is all going to be the same because this particular molecule would be sp3 hybridized with a tetrahedral geometry. Okay, and so again, if you're not sure what I mean by that, the way to identify it on the chart, you're looking at how many things are bonded to our central atom right here. So if we look at this chart, which I know is a little bit blurry in the presentation, we know there's one central atom and 4 things that are attached to that central atom. So we would go down to steric number 4 right here, and we would look at our central atom to determine if there's any lone pairs. It doesn't look like there are on this particular molecule, so we would be a tetrahedral geometry according to this chart. Now, the other chart that I gave you has a little bit more information, and you would find if you looked over to the hybridization column that that particular molecule would be sp3 hybridized, which is going to tell you what is happening with those electrons within those bonds. Okay. In terms of polarity of the entire molecule, you can represent individual bond polarities or the polarity of the entire molecule. So what you're seeing here in these little red arrows is a polarity in an individual bond. But if I were to draw the polarity of the entire water molecule here on the left, I would draw my dipole moment like that because oxygen is more electronegative than hydrogen is, and there's some lone pairs up here, which would cause my dipole moment to look like that. Okay. Again, we have a individual bond polarity represented by that arrow, but if I were to draw it for the entire molecule, it would be in the same direction, just like that. This molecule here does not have an overall dipole moment because though these bonds are definitely polar, there's fluorines all over this molecule. So this one doesn't have any overall dipoles. This molecule would be non-polar. All right. And then same story with this one. We see polar bonds pointing in either direction, but overall, there's no difference in electronegativity from one side to the other of that molecule. Our lesser electronegative atom is in the center. Okay, so to talk about hybridization and hybrid orbitals a little bit, because I've mentioned that a couple of times. Sometimes orbitals are going to smush together and become kind of like this mutant orbital. And that's what we call hybridization. So s and p orbitals are not equivalent in energy. So to bond successfully, atoms need to hybridize their orbitals. And again, that just means smushing together and making a weird mutant orbital that's a combination of both of those. Okay. So how they're going to do that, the pattern at which they do this, is determined by the number of electron groups around your central atom. So if we recall from our chart, by electron groups, I'm not talking about lone pairs, right? So something with like say CH4, which looks like this, our 4 hydrogen atoms count as 4 electron groups that surround the central atom. Just like in NH3, we have our lone pair up top and we have our 3 hydrogens around. This nitrogen still has overall 4 electron groups surrounding it. One is a lone pair, the other 3 happen to be atoms. But again, the electron groups are the same. So that's why if you look on the VSEPR chart, you will find that a tetrahedral molecule has an sp3 hybridization, but so does a trigonal pyramidal molecule because they have the same number of stuff around the central atom, okay? So I have embedded a video within the presentation that I did show you in class. If you want to look it up on your own, it's Professor Dave Explains Hybridization. I highly recommend that video. He's very good at explaining how this all works. I'm not going to show it within the video right now. You can look that up on your own. So modeling orbital overlap between atoms that are bonded together. You can have what's called a sigma bond, which is a single bond with high electron density around the central bond axis. So that's what you're seeing represented over here in green, a sigma bond. Or you can have a pi bond, which results from 2 overlapping unhybridized p orbitals that are perpendicular to your bond axis. Okay, so that's what's being represented in blue over here. Those would be pi bonds. So as in class, I'll tell you again, sigma bonds are end to end. So I like to say that those 2 orbitals are punching each other in the face, and you can see that they're literally end to end and they're overlapping right here in the middle. Whereas pi bonds, these p orbitals up here, it was mentioned to me in class, they're high-fiving from a distance, right? You don't see them touching each other in this diagram, but over distance, they're still able to share some electrons there. So when you see something like this, what's actually happening is these p orbitals are kind of blending together and they form this really messy looking cloud above and below, if I were to represent that, but we don't showcase it like that when we draw this out because that would be really messy and you couldn't see through all the shading that you would have to do. Okay. So one more thing to know about these type of bonds, single bonds are going to express sigma, right? Only sigma. There's no pi bonds within a single bond. However, double bonds are going to contain 1 sigma and 1 pi bond each, and triple bonds are going to contain 1 sigma and 2 pi bonds. Okay, so what we're looking at here on the left is 1 sigma bond and then 1 overall pi bond. And you know it's only 1 because p orbitals have 2 little groups here, a bonding and an anti-bonding orbital. So 1 set along 1 axis is going to be 1 overall pi bond. Okay, if there had been another set of orbitals here on each axis, as I'm drawing in right now, and then they were sharing across distance as well, that would be 2 pi bonds, indicating a triple bond. But on the left here, without all of that information drawn in, we are looking at a double bond overall. Okay, so here is a double bond. Once again, the orbitals are color-coded for you, so it's kind of nice. We're seeing in a double bond, again, which is represented by 1 sigma and 1 pi bond. Here's the sigma bond in the middle, and then here are our p orbitals that are going to share over distance. So that together is 1 pi bond. All right, and then down here you can kind of see they're leaning towards each other a little bit and forming that weird mutant looking cloud down there. So to compare that to a triple bond here, which is represented by 1 sigma and 2 pi bonds, again, we see in the middle those 2 orbitals punching each other in the face and overlapping there. And then our p orbitals, we have the ones that are going to be on the same axis that I'm currently outlining here. So we see sharing and sharing, and that's one of the pi bonds. but the other one happens between these two that are kind of behind a little bit. You can't see them as well, but those are going to share as well. So that's going to be our second pi bond. And again, down here, you can see it kind of leaning towards each other, forming a weird mutant cloud over there. Okay. So to look at an example molecule, ethane, if we draw out the original Lewis structure that we're all used to seeing, we can see that in ethane, there is a single bond. Given what we know, and I just told you about single bonds, that should be a sigma bond between those two carbons. Okay, so how do we represent that? How do we draw it out? Is the first question that you should be asking yourself. So our first step is to figure out our molecular geometry around each central atom. In this case, there are two central atoms, each with their own unique geometry. So if we were to cover up half of this molecule and pretend that the stuff on the right doesn't exist, if we counted how many things are bonded to this carbon, we would get 1, 2, 3, 4 things overall bonded to that carbon. Okay, which means that that carbon on the left has a tetrahedral geometry, right? And if we look on our chart and we look at the hybridization pattern for a tetrahedral geometry, we find that that carbon on the left has an sp3 hybridization pattern. The same can be said for the carbon on the right. Both of them have sp3 geometry because, again, we cover up what's on the left. There's, again, 1, 2, 3, 4 things bonded to that carbon. So it has the same exact geometry as the carbon on the left. Okay. The next thing to look at really is the electron configuration of your centrals. So carbon has an electron configuration of 1s2, 2s2, 2p2. Okay. The 1s2 is core electrons. So we're going to ignore the existence of those core electrons because they're not going to participate in the bond. And we're going to draw out the orbital diagram, or the arrow diagram, as I like to call it, for the valence electrons, which are the 2s2 and the 2p2. So drawing that out, our 2s2 is represented like that, and our 2p2 is represented like this. Now, when these two things hybridize, because that's what's going to happen, because again, we're sp3 hybridized, this electron, this downward spin electron here, is going to get promoted over, and it's going to get promoted to p. So realistically, what you end up with is something that looks like this. And then those two orbitals are going to overlap and become an sp3. Now, how do we know that all of them hybridize and nothing is left out? Well, for sp3, we have 1s and 3p electrons. And since we promoted one of our s's to a p, we have 1s and 3p electrons. So that's how we know that all of them are going to be involved here. Okay. So for each carbon, just like we always knew, there's 4 electrons that can participate potentially in a bond. Obviously, 3 of those are going to be bonded to a hydrogen, 1 for each hydrogen, right? So one of those carbon's electrons is going to send toward the first hydrogen, the second, and the third. And then same on this side. 1, 2, 3. Okay, so that's 3 out of the 4, right? For hydrogen, and I'll switch colors for that. Hydrogen only has a 1s1 electron configuration. It doesn't have multiple orbitals to hybridize anywhere. So hydrogen's orbitals are spherical and they're going to overlap. And that electron share is going to take place in those bonds. Okay, so I'm just going to finish drawing in my electrons. All right. Now for what's happening between the carbon and the other carbon. Well, we have 1 electron left on each side, right? So this carbon's going to extend into the center. That carbon's going to extend into the center. There's going to be an electron extended from either one. Those orbitals punch each other in the face directly. So we call this a sigma bond. Okay. If you have questions about that, I'm happy to go over it again with you in class. Moving on though, to our next one. This one's a little bit more complicated because this is a triple bond. And we know that triple bonds have 1 sigma and 2 pi bonds, right? So there's something complicated that's going to happen in the center here. Okay. So once again, we're going to figure out what the geometry is around each central atom, which again, both cases, it's carbon still. We're going to figure out the electron configuration, hybridization. We're going to start drawing. So this is a linear molecule, right? And we know that because there's only 2 things bonded to each carbon. So if we look at our chart, we would find that that's linear in shape, and therefore it's sp hybridization. Okay. Carbon still has the same electron configuration as it always did, R1s2, 2s2, 2p2, right? These are still core electrons, so we're going to ignore their existence. We still have our initial orbital diagram or arrow diagram that looks like that. But now what's happening is we have a different hybridization pattern. It's just sp according to our charts, not sp3 anymore. So this electron, this downward spin, is still going to get promoted over, and we're still going to end up with this situation happening. But this time, not all of our electrons are going to participate in that hybridization, okay? Now, since it's an sp pattern, there's only 1 s and 1 p that's going to hybridize here. So that's going to be these 2. It's going to hybridize into our sp. And we have 2 p electrons that are left out unhybridized per carbon, okay? 2 that are left out overall. So I'm going to erase this and I'm going to move it, actually. I'm going to move it somewhere else so that we can draw easier. All right, so our hydrogens still don't hybridize anything because they're spherical. They just have that 1 s electron. We are looking at from each carbon 2 electrons that are in that hybrid state, right? One of those hybrid electrons is going to extend out towards the hydrogen, 1 on each side, and one of them is going to extend in the center, okay? So we have there, we have that happening. Okay, so once again, when our electrons are punching each other, when our orbitals are punching each other, I should say, we have that sigma bond in the center, we have a sigma bond here, we have a sigma bond there. All right. So in that triple bond, our 1 sigma bond is accounted for. But we also have our pi bonds that we have to worry about. Now remember, for each carbon, we have 2 p electrons that are unaccounted for still. So we're going to draw in, and it's going to be kind of small on the bottom, I apologize. We're going to draw in our py. Now, why is it called py? Because it's on a y-axis. So if we were to superimpose a graph over this, we would find that that vertical axis is a y-axis. So that's why it's called py. Okay. So we have sharing happening between our py's. And again, I know it's a little hard to see on the bottom. But that only accounts for 1 of our remaining p's on each carbon atom, right? So we need, in addition to that, we need a pz orbital, which I'm drawing at a diagonal because it's in the z plane. All right, so I'm going to label that pz, pz, and we're going to get some sharing happening between both of those. So that represents our second pi bond. The pink one is going to be our first pi bond. The orange one is going to be our second pi bond, which accounts for the 2 pi bonds that are present within a triple bond. Okay. So again, if that was confusing for you, I really want you to talk to me about this in class or in ELT, but I hope that was somewhat helpful and you can refer back to this.